All right. Hey, guys. Good to see you right now. I'm going to make this nice and quick because this isn't really a lesson day. This is just kind of a quick thing that I didn't tell you on Wednesday's lesson, but does come up on the problem set for this weekend. And that has to do with what we're looking at in front of us here. So it's going to set us up for something called the corollary of the basic proportionality theorem. Now, it's been a while since we had a corollary. So just to remind you, a corollary is a theorem that follows pretty much immediately from from a theorem that maybe we've proven already here. So, of course, last class we had the basic proportionality theorem, and that one was where we have these two parallel lines right here, right? Two parallel lines right here. And one of the parallel lines is intersecting two sides of a triangle, right? We have that here, and we have a triangle right here, and then we have a line that's parallel to one of the sides of the triangle. Well, that line here is going to divide the other sides of the triangle proportionally. Ergo, RP to PT, right? That ratio here of r distance RP to distance PT is going to be the same as the ratio of SQ to QT, right? And we can bank on that. We know that's true because that's a theorem here. Okay, so that was the basic proportionality theorem. What we have right here in this hopefully quick video, because again, this isn't a lesson day today. Hopefully you're putting this in your notes. Hopefully you're watching this video because it's going to come up in the problem set this weekend. But anyways, what's going to happen here, the corollary of the basic proportionality theorem here, do we see any triangles in this diagram? Come on, guys. We see any triangles? Okay, so it doesn't have to do with triangles, right? Like the basic proportionality theorem had here. So this has been an extension that follows from it here. Okay, so maybe we start thinking about this. We have the diagram. I've already put the given up there for you, right? You should see in the diagram too what types of lines we're talking about here. Okay, we're not talking about triangles. We're not talking about two parallel lines. What are we talking about here? Well, if we have three parallel lines. Okay, so if we had to predict maybe the wording here of the basic proportionality theorem, I just really want you to look at this diagram here and kind of belabor that point that like this diagram here is going to be very darn similar to what this one is, something that we can prove given we have a triangle and there's two parallel lines. Here we don't have a triangle, so this is just given. If given three parallel lines that do what? What do they do? Okay, can we think about the proof here in a second? Well, they are all cutting, right? The three parallel lines are cutting two transversals. Okay, if three parallel lines cut two transversals, what do you think the big conclusion is going to be? What do you think here? What do you notice here? What do you notice visually, perhaps? What are some guesses that you have? Okay, if three parallel lines cut two transversals, then it looks like we create some segments. And what do you think? Well, we had a proportion here. Are we gonna have a proportion here? You sure as believe it. We're going to have a proportion here. And let's check out that proportion right now. There we go. Corollary of the basic proportionality theorem. You have three parallel lines. That parallel line in the middle here is going to divide the segments running between the two parallel lines proportionally. And it's just kind of cool, right? RS to ST would be the same ratio as XY to YZ. Let's look into some algebra problems in your problem set tonight. Let's check it out here. Let's get it worded out for you guys to have this. You can put this into your notes again. Try to stay organized. I know that mystery writer will be putting this up in the chapter 5 section of that Google Doc that's like 10 pages long of everything we've learned this year. But anyways, you should put it in your notes too as well. If three parallel lines intersect two transversals, then they divide the transversals proportionally, okay? So I don't really like this wording a little bit here. I kind of stumbled across this when I was trying to describe it here because transversals are lines, right? And lines can't get divided proportionally. I guess kind of the segments gets divided proportionally. Okay. So, anyways, right, a line can't really be divided proportionally because a line goes on infinitely. So here, point S is going to divide segment RT proportionally as Y divides XZ in that same ratio. Okay. So that's what we have here. We have these parallel lines. We can take it. We can go ahead and run with it here. We would have some intelligence here. We got three parallel lines. I know this, I know this, I know one of these. I can figure out the other thing. And that's really what we're going to work for in the homework this weekend and whatnot here. All right, so I know you guys are zoning out. You have a homework problem set to do. You don't want to I don't want to listen to another proof or whatever here. Guys, the proof of this one is super easy. I do think you get something out of learning from your instructors or seeing your instructors lay it out, be like, this is a theorem. Well, you got to ask, where's the proof for it, right? How do I know this is factual, right? We should be able to write a proof, and we can. We can do this pretty easily here. So try to follow my logic as we kind of see here. Let's review something. Let's review something called introducing an auxiliary set. That sort of is going to be the big trick as to how this actually really connects to the basic proportionality theorem. Okay, so remember, basic proportionality theorem, what did that have to do with? Didn't have to do with 3 parallel lines. It had to do with what? We just talked about it 5 minutes ago. Had to do with 2 parallel lines, right? Where one side is one side of a triangle, or one parallel line is one side of a triangle, and then that other parallel line is sort of intersecting those 2 other lines, right? Dividing those proportionally, okay? So this here, right, a corollary is going to use that theorem that it's based off of, okay? So this is the corollary of the basic proportionality theorem. So what do we need to do to maybe use the basic proportionality theorem? We need to find what in our diagram, right? Basic proportionality theorem had to do with triangles. Do I see triangles in this diagram up here? No, I don't see any triangles. We need to introduce triangles to this diagram. So there sure are triangles up there. We just don't see them yet. What do we have to do? We have to draw them in. We have to draw them in. So check this out here. I'm going to do this. I'm going to draw segment TX. I got my pen right here. I'm going to draw it. Draw TX intersecting SY at ends, okay? That's kind of confusing here. Draw segment TX, okay, right here. Ooh, if I draw a triangle like this, mind blown, because that triangle right there, gonna be divided proportionally. That's, anyways, we'll see in a second. Draw segment TX intersecting SY at ends. So that really is just, so it's basically naming a point there. You don't really need to worry about that second part. The big thing is just, they're telling you to draw TX. Okay, I can draw TX. Why am I allowed to draw a segment between points T and X? Why am I allowed to draw a segment? Well, through exactly 1 point, through 2 points, exactly one line can be drawn. So that's called introducing an auxiliary line through 2 points, okay? So we did that one kind of lesson last semester where we talked about 4 or 5 auxiliary sets they add to diagrams and proofs, and you might have to add those too, okay? So justification here, I drew it in. There we go. There it is, drawn in right there. Justification through 2 points, exactly one line can be drawn. Check it out. That's pretty neat, because what do we see here? I should shade this in. I should show it to you here. Look at this. I got triangle TXZ, and check it out. I don't know if you've seen this yet. Mind's going to be blown when you see this for a second. I have triangle XRT. They both share line XT, and we know this point N here, right? This is going to be this NT to NX has to be the same as ZY to YX. Why? Basic proportionality theorem. Wait a second. I'm not done with segment NT and segment NX, because distance NT to distance NX has to be the same as distance TS to distance SR. Why? Basic proportionality theorem. We have this here, SN, here, it's not a mid-segment, right? We don't know if it's a mid-segment or not, but it kind of looks like a little bit here. So remember, basic proportionality theorem, that's just a parallel line cutting through that triangle at any point, but parallel to the third side here. So SN, clearly not a midpoint, it's closer to point T than it is to really R down here. But anyways, SN is parallel to RX here, okay? So it's parallel to this RX here. So in this triangle here, TRX, SN would divide segment RT and segment XT proportionally, right? Meaning TS over SR equals TN over NX. Anyways, let's start writing this out here because the proof is super short. Let's just kind of get it all done here. Next step is what? If you're following my logic, next step's what? The basic proportionality theorem. Let's get those proportions written out right here. Boom, basic proportionality theorem is joining us here. And let's move myself out of the way. So that's the reason why this is the corollary of it. We're extending this here. We introduce these triangles so we can prove this just for any 3 parallel lines. This is going to be true, right? That it's going to, that second parallel line in the middle divides those transversals proportionally here. So here is kind of what I was discussing a little bit earlier here, right? RS to ST is going to be the same as XN to NT, okay? Because that triangle right there, if we apply the basic proportionality theorem, this to that is the same as this to that, right? These 2 sides, which are not the third sides being parallel to, right? That kind of thing here, okay? So right, maybe you're trying to connect these things together. Maybe that's where brain's going. We'll get to that in a second. We can also say, what about, so here's XN and NT. We're repeating XN and NT because, again, XN and NT is a side of another triangle where this segment, this line NY is also going to divide those 2 sides proportionally. So we also know that XN to NT equals XY to YZ. Those would be a common ratio between those 2 sides here. So it's in a proportion, okay? Basic proportionality theorem, well, hey, this ratio equals that ratio. And that ratio, it's back over here, it equals another ratio, okay? So that means that this ratio would have to equal this other ratio over here. Why? What's the reason for that one again? Guys, we've been doing it all year. What is that? When two things each equal the same thing. Look at this here. Xn over nt, xn over nt. Those are the exact same thing. They're not just equal to each other. They're the same thing reflexively. Okay, so this here is when two things are equal to each equal the same thing, they are equal to each other. That is the great rule of transitivity, right? Abraham Lincoln, big fan of that one. We talked about that last semester. Okay, so by transitivity, I can set Rs over St equal to Xy over Yz. Boom, the transitive property of equality, and then that's it, right? We got there. Check it out. We just finished it. We got to our what was we were trying to prove right up here. Okay, when we have three parallel lines and we're cutting two transversals, those two transversals will be cut in that proportion. That's true. Okay, this to that equals this to that. And without further ado, I think you can start your homework right with this stuff here. You don't have to stick around, but I will maybe show a couple things that appear in your homework. Because guys, problems involving the corollary of the basic proportionality theorem, they're pretty darn easy. Okay, pretty darn easy. Because they're pretty much the same, right? The basic proportionality theorem problems that you'll have in the problem set this weekend, you're going to have triangles, right? You're going to have triangles. One thing's going to be parallel to the third side. Those two other sides are going to be divided proportionally. Here, this isn't a triangle, right? We're not looking at triangles here. Sure, if I extended that, there's a triangle. But hey, this is the same thing applies here, okay? Stated proportion for each diagram. Well, that's super easy. You have this, I think, in your problem set this weekend here. That's why I'm doing this video here. Stated proportion, well, I can just do that. 15 to 10 equals y over 14. Look, this to that equals this to that, right? So it gets divided proportionally right there. So that's pretty neat. Okay, so you can actually solve this problem, right? So it just says stated proportion, right? That's a proportion. We're done here. Okay, this is in a 3-to-2 ratio though. So this has got to be 21, right? Because that would bring me into a 3/2 ratio here. Because this is 1.5 times larger top, 1.5 times. There's a lot of ways you can do it faster here. But you can also just cross multiply, right? 10y equals 225 is 15 squared. So what does it take away? 210, right? Equals 210. Anyways, 210. So 10y equals 210 divided by 10. Yeah, it's 21 here. Okay, so y is 21. But you didn't have to do that. You just have to set a proportion. So super easy, guys. Super easy. Look forward to that. More problems like that on the homework, hopefully, but maybe not. All right, so let's look at this next one here. So yeah, I don't know if this might be on your problem set on Monday or Tuesday. I forget what your next problem set is here. But anyways, here's another basic proportionality theorem. The corollary of the basic proportionality theorem diagram right here. So it's saying state whether the proportion is correct. Could you make an argument that it's correct here? D to E. Okay, so I would set it up. D to E equals F to G. Okay, so that looks like that's going to be, well, they don't have any of them here, but I know that this one's going to be correct. So that one's correct because, hey, that's just a mean swap. Check it out here. So D to E equals F to G, right? That line here divides this transversal, this segment of the transversal, proportionally to that segment of the transversal because that line's parallel to the two other lines here. Okay, so that one's correct because there's a mean swap. So this is sort of the basic thing I would deduce from that. But then remember, we can set up a whole bunch of other proportions that are correct here. Look, D to F, okay, right? This here, so so you can use this like top parts. This top to that part equals bottom to bottom, right? Very similar to the ways we can manipulate the basic proportionality theorem, okay? All right, so this is true. Let's see here if we can justify any of the other ones here. F to G, this is F to G equals E to D. No, that's false. F to G would go to D to E. So here this is similar to this here, the same thing here, except FG didn't flip over. DE flipped over. So that one incorrect. Okay, that one's incorrect here. What about D to F? Okay, D to F is good. I like that. It's the same thing as E to G. Yeah, totally. That one's good to go. I thought we already kind of did that one here. No, wait. Oh, I was wrong about that one here. Okay, I got tricked on this one here. No, this one's wrong. I was like, we did that one already. Yeah, no, here, this looked pretty much identical here. This to that should equal this to that, right? Not this to that equals that to this. No, it doesn't make sense, okay? So this is sort of like, looks like these segments are a little bit longer, right? You can think about it that way. So this is long to shorter equals short to long. That doesn't make sense, right? It doesn't make sense here because that one's false. Okay, C is G to E, and I'm guessing it's going to be true because the only one's true so far is D. But anyways, G to F equals E to D. Yeah, I'll agree with that. Yeah, I'll totally agree with that here. How can I justify that? So G to F is right here, so maybe I just flipped it over and I flipped this one over. Yeah, I inverted this fraction, right? This fraction here. Okay, there are a whole bunch of things we definitely say. We could also say, right, if this were X right here, okay, and this is y, we can do the whole part, the whole thing, and have fun with that, right? Because our denominator adds would justify that. So we could say y to g equals x to e, and we can drop the mic and all this stuff like that. And hooray, we know our geometry now. All right, email me if you have any questions. Thank you guys for watching this. Sorry you have like another lecture. I'm trying to cut it down a little bit this semester, but basic the corollary. We'll get the corollary out of the way, and then we just have one more theorem left in chapter 5. You'll learn about that on Monday. Hey, the triangle angle bisector theorem. Look forward to that. Okay, good luck with the problem set this weekend. Email me if you have any questions. I'll see you guys Monday.